Happy for you if you're not in a cold place. But Dave and I are, so just enjoy it. It's a bit of hibernation weather. So today is another SASA Spatial Statistics Interest Group seminar. And we have the pleasure of Dr. David Rose giving us a presentation today on geostatistical support. So David is currently a senior lecturer at the University of Witwatersrand. He's originally from Durban, where he got his BSc and BSc honours, together with Pravesh, who is not here today. He's unfortunately stuck in a very boring funding meeting. He apologized for not being here. David majored in mathematical statistics, and then which was then called the University of Natal. His master's dissertation also there, as well as his PhD, which he spread his wings to go to the University of Cambridge in the UK, was in the area of queuing theory and queuing networks. After his graduation, David worked at De Beers in Johannesburg and Toronto, where he gained on-the-job experience in geostatistics. So as if you don't know, geostatistics was born in mining, specifically in South Africa. And he has a formal qualification in the field from the Center of Geostatistical. I'm not French, so obviously said that wrong as well. He is now a senior lecturer in the School of Statistics and Actuarial Science at WITS, and he recently became lecturer in honours course in spatial stats. I think WITS is one of the few universities, there are others, who are doing spatial stats in their statistics curriculum. And I think this will grow immensely as we go forward. So thank you, David. The floor is yours, and we look forward to hearing a bit more about geostatistical support.
Okay, thanks.
I think you're going to change it now to full screen mode. I'm not sure if it's frozen.
It's supposed to be in full screen mode.
Seems frozen on my side. Maybe I'd stop sharing and share again.
Oh, you want me to exit and go back in?
I think so. I don't know. Is anyone else also seeing a frozen screen?
Yeah, it's also frozen for me.
Okay, there we go. Thanks, Renata. Yeah, I think David, just unshare and then share again. And Stefan said as well.
Okay.
Oh, Linda Haynes is here. We are graced. Hello, Linda.
Hi, Anna. How are you?
Good, lovely to see you. Thank you for coming.
Sorry I'm late.
No, we've only just begun. We've just begun. Okay. That's perfect,
so,
David.
Is that any better?
Perfect. Thank
Okay,
you. Over
great.
to you.
Okay, hi everyone, and thanks to Inga for the intro. So yeah, I'm going to obviously be speaking about the idea of support, particularly as it applies to geostatistics, but it does have wider relevance, I guess, to other spatial statistical contexts. But my focus will tend to be on the geostatistical elements. So just a basic idea of what I am going to cover is obviously to introduce you to the topic, then provide some motivation for why it's important to look at the idea of support. And then from the more practical aspects, I'll move on to some of the statistical / mathematical formalities expressing support in a more mathematical fashion. And then lastly, I'll wrap up with the conclusion to solidify the ideas. All right, so just to demonstrate the point, I'd like to turn to an R package, R software package, which you may be familiar with. It's one of the main spatial statistics packages called GStat. All right, and it'll become clear to you in due course why it is that I'm looking at this particular one. I chose it because it homes in on exactly some of the topics or some of the relevant aspects of support. So can you see my mouse when I move it?
Yes, perfect.
Okay, great. So you'll see as part of the description of the package there that they talk about point or block kriging or crow kriging. So this is the manual, obviously, and further, I just make sure that I acknowledge the source of this, so no one can accuse me of plagiarism or anything. So that's just to type all the legalese, I suppose. But what I want to look at is another aspect of the manual, which talks about Dani Kricher, Prof. Dani Kricher, who passed away a few years ago. So it says he is a South African scientist, but I guess he was a South African scientist, unfortunately. So that name may ring bells for you. He was a mining engineer. He also lectured at Wits. And it was after him, again, that you may know that a person, someone by the name of George Mataron actually gave the name of this particular interpolation method, as again you possibly know, which he called kriging. Now, George Mataron was at the place that Inga was a bit too reluctant to pronounce, but basically he was, he also passed away a few years ago, but he worked in France, in Fontainebleau, at the Center of Geostatistics. It's changed its name a number of times, but the fact is it's one of the places where geostatistics developed. And Dani Kricher, as you could tell by the mere fact that his name has been given to this procedure of kriging, obviously played an important role as well. So also some of what I'm going to show you is of relevance to mining, because as Inga mentioned, I did work at De Beers, and this is where the concept became more familiar to me, as well as at the George Mataron's Center of Geostatistics. All right, so that's, as I say, just a note that is put into the documentation for this particular package. Now, moving on then, again, the particular function of relevance to kriging in this package, not surprisingly, is called Kricher or Krig. Okay, and again, you'll see the point or block kriging or simulation appearing. And again, so this issue of block kriging and point kriging appears a number of times in this particular documentation, and obviously that is one of the main types into which you can separate out kriging. So on the one hand, you might have simple and ordinary kriging, which are reliant on particular assumptions about the data you're dealing with, or the field or domain you're dealing with. But then on the other hand, within pretty much each of these types of kriging, be they simple, ordinary, or universal, you do have the option, in inverted commas, of looking at either the point approach or the block approach. So that's a very vague mention that in a very vague terms, but obviously I will qualify what I'm talking about in a short while. And on this slide, you'll see the parameter block. Okay, not surprising, again, the terminology. So at this stage, we're in the R package called Gstat. We're looking at the function Krig, and now one of the parameters of that particular function is called block. And this is why I've been spending a bit of time on this package, because if you look at this last sentence here, it's written that by default, predictions or simulations refer to the support of the data values. Okay, so here you're seeing the first mention, at least in what I've shown of this package, of the idea of support. So just remember that they say there, predictions refer to the support of the data values. So let's delve deeper into that idea. So again, recurring theme. We have point kriging and block kriging. And what I've done in this on the slide is in the two figures is I show in red the target, the place at which the location at which you want to estimate a random function. And then all those in blue represent the samples. And what hopefully you'll notice is on the left-hand side, just as we mentioned now in the GStat package, your target in red is of the same, what is called the same support as all those blue samples around it. And then on the right-hand side, the transition to what is known as block kriging, something I've mentioned quite a few times, is that the samples are of one, in inverted commas, size, and then the target, the one for which we want to estimate or predict a value, is considerably larger. But the first point about this is support is more than purely about size, okay, of target and of samples. So I'll look at that shortly. But what I do also want to focus on is that if you have done any kriging or anything of this nature in geostatistical support, what I realized over the years, particularly after my stint in France, is that that term of point can be misleading. Because when we were required to do a project as part of that program that I did in France, and the idea of point, as I say, can be a bit deceptive. And it took me a while to realize that this terminology was perhaps not ideal. In French, it's called criage ponctuel, which I imagine you can hear the punctual or point. And I think sometimes what happens as well is that there's occasionally cases of lost in translation between the French and the English, or at least I think that could be part of the reason why some of the terminology in English doesn't necessarily convey the same meaning as it would in French. But long story short, as it was said in the GStat package, point kriging does not literally have to refer to a single point. It is merely the case that, as you can see from that diagram on the left, the points, the samples, and the target are of the same, as you'll see just now, support, or if you want to look at it more vaguely, of size in a very vague hand-waving way. Okay, so it's not so much points or blocks as it is the relationship between the samples and the target. Okay, so hopefully you've followed what I've said, and please feel free to ask any questions as we go along. Inga, if you can just tell me if there is anything in the chat or so on, because I'm got a full screen dedicated to the presentation. So if there are any questions, please let me know. Anyway, so to summarize so far, point and even block kriging can be a bit of a misnomer, and support is what underpins these definitions or these terms for kriging. So now we move on to sampling. Why can support be an important concept in practical application? So I'm not expecting you to be necessarily a geologist or an expert in diamond mining or anything, but essentially what I want to point out in these figures is what you get in the top left is what are called core drill holes. And you can see I think the picture gives a sense of their relative size. when you compare it with on the top right is what has been drilled there is a larger diameter drill hole into the ground in order to, in this case, determine, look at samples of diamonds, but similar principles would apply to other commodities. And then, although it's not so obvious, at the bottom there is what is called bulk sampling, where you are talking about considerably larger coverage than either of the two up top. So the main takeaway from this slide is that not all samples are of the same support. Again, I could imprecisely use the term size. But the fact is, when you are, and leading on from that, when you are going to do estimation, such as you would with kriging, it is, as a general rule, it's not appropriate to mix different supports without, as if they were all the same, without actually taking into consideration that they are not all of the same order of magnitude. Okay, so any questions so far, Inga, from the chat or anything?
Nothing. You're
okay,
good.
great. So then I'll continue. So what I'm now going to show you is my example of drill holes. So what we have there is, in each of these, obviously it's a toy example, we have our 3 different types of drill holes, and you basically have, in each of them, you have 3 samples. Okay, so you have your, obviously on the left, the far left and the far right, you have your vertical drill holes, which is practically what does happen. And then in the middle, you have a drill hole which is not vertical, it's actually slanted. And again, this is practically what can happen. It's just a case of optimizing cost and time and a sampling process in order to achieve the best that you can. And also sometimes some of these drill holes have a dual purpose of mapping or modeling not only the geostatistical elements, but also the resource you're looking at, the mine, or other geological entity. You might also determine the nature of that deposit with the help of these drill holes. But the main focus here again is on the geostatistical nature, what we want to look at. Okay, I've been a bit maybe not so precise with the notation, but basically we have there a random function, a z, which hopefully from a spatial perspective or the theoretical aspects you're familiar with. And what I should have mentioned as well is that this is more generally applicable than just to mining. And of course, as geostatistics is more generally applicable to meteorology, hydrology, even fish in the sea, but definitely also oil, petroleum, and mining. Okay, so I'm going to just assume for the purposes of this exercise, the random function will, for example, be a grade or density. Okay, gold grade, you're probably familiar with, carats per cubic, carats per grams per carat, sorry. Oh, I might have mixed that up, but hopefully you get the idea. Okay, so here sitting in the blue on the left-hand side, you have I've isolated or focused in on a sample. And then in the middle, a drill hole, a green sample or sample rendered in green. And lastly, on the third drill hole, a purple sample in a purple color. Okay, so what you'll notice, well, hopefully will notice, is that the blue, green, and purple samples are of the same, effectively of the same dimensions, and certainly the same volume, and consequently probably the same mass, assuming that the density is constant across them, across all of these drill holes. So if I now call the fact that the blue is not a point in conventional or regular sense, we're going to call that blue sample V, which is to indicate V for volume, that it is a coverage of more than just a point, which again brings us to the issue of point and block kriging, but more of that later. So now let's call our purple and green samples V prime and V double prime, again with the sense of V representing volume. And I should also mention that when we talk of volume, as probably you do in maths as well, volume does not necessarily in this context have to mean a three-dimensional, if I use the word loosely, the content of a three-dimensional entity. All right, this can be extended to theoretically many dimensions, and also in the other direction, in a two-dimensional scenario, it would be an area, and then in a one-dimensional context, it would just be your actual point. All right, so the term volume does not necessarily, just to repeat, it does not necessarily have to refer only to three dimensions. The principle extends to those other instances. All right, so if I now translate this blue sample by a vector of H, you can clearly see in the next slide that although they might be dimensionally similar or the same, the translation of V to V prime, they do not overlap. There is an points of overlap, but there are also points which do not overlap. However, if we then go on to going from our blue top on the right, left, to the purple on the right, you will see that translating the sample V and V prime through a vector translation of H, or a lag H, the two coincide, the two overlap. And this is effectively the difference between being of the same support and not being of the same support. In a nutshell, if you translate one volume or one entity through a lag or a vector of H, and the two cones, and it is possible for the one to be derived from the other through a translation, then they are said to be of this. Those samples are said to be of the same purport, the same support. So again, I emphasize it's not only about size, dimensions, volume, in the conventional sense. It's also about the other elements to the idea of support. Okay, that's just this slide just emphasizes that the one sample on the left can be achieved or can be translated to the sample on the right through this vector H. All right, and I pretty much said what are on these next two slides, so I'll move on then. And emphasizing the point yet again that the mere fact that volumes or masses or dimensions are the same does not in general imply that the support is equal. right? And like I've said, or as you've seen, other criteria like shape and orientation and space also contribute to whether you're talking about the same support or not. Now, what does that mean in a practical sense, or rather in a theoretical sense? When you Krig, or even when you determine your variogram models from experimental variograms, even though you might have similar dimension, the fact is that if you do the mathematics behind determining a variogram at different supports, you can't simply work on the assumption of equality of volumes. The mere fact is, when you work with integrals, okay, to account for this change in support, the integrals will also need to account for direction, for shape, and so on. In other words, as hopefully you're aware with integrals, there's more to it than purely dimensions. You might have to do a rotation, or for instance, in order to get them in the same plane or on comparable planes. But the fact remains that there is a transformation that has to happen with the integrals so that you are comparing, in inverted commas, like with like. But perhaps I should rather say that support will, in a nutshell, support will influence the calculation, as I said, of your Kriging estimates, and even, as I say, will influence your calculations when it comes to variograms. So let me be a bit more specific in mathematical or statistical terminology. Okay, so we've seen the intuitive idea that support is all about translation. But now let's formalize that in terms of notation and mathematical jargon. So what I'm going to do there in this slide is I'm going to write the collection of a number of volumes. I'm going to write as that calligraphic V. And what I'm doing now is I have a domain D, not V, D, and I'm partitioning that domain into a number of volumes. And obviously by partitioning, I'm saying that it's a disjoint union of these volumes, and also the union of those volumes must end up being exhaustive. In other words, it constitutes the entire domain. Now, what you might also notice here is this is not that unlike the idea of lattice data, where you have sub-areas, or in taking the union of these sub-areas, you end up with the full area or perhaps the domain. So the concepts are analogous, okay? And then again, in the next paragraph, I indicate again that volume does not have to mean a volume in 3D. And so we've talked about the overarching idea of this collection of volumes. But if we now identify a single one of the volumes, what it means, and again, there's some overlap a bit with the lattice data concept, is that that volume is made up of a number of points from the domain, typically and practically contiguous points. And then, as with lattice data, you provide a point to represent that volume. In other words, it's typically maybe a center of gravity, maybe a literal central point, but some idea that in the same way that a histogram bin is represented by its intermediate point, its center point, by the same token, you would allocate this volume a location or a point which is representative of the entire volume. Okay. So now, again, in more formal language, a volume whose center or representative point is S prime, and it is one of one of the partition elements of the volume, it is said to have the same support as another volume located elsewhere if and only if that first volume can be represented or can be represented as a translation of the other volume. And that is what I showed you when we looked at the drill hole example. So now let's go a little bit further into the mathematical description of the support. Okay, so in actual fact, hopefully at least some of you will remember from undergrad maths, probably undergrad maths, about the concept of an equivalence relation. So if R, that fancy R over there, represents this relationship, the wording that I've just said on the previous slide, that the volume, again, I'm going to loosely say centered at S prime, is related to the volume, in other words, related through equivalence of support to another volume, again, loosely centered at a point or a location S. Those two, the relationship holds if and only if there is some lag vector from the appropriate dimension such that the volume of that V of S prime can be represented as V of a translation of S through S, the location S, through a vector H. Okay, so that is basically what I said on the previous slide and what I demonstrated in the drill hole example, where I shifted different colored samples across the screen or from one drill hole to another and indicated to you in the conditions under which you have the same support or not. So deep diving a little bit further into this relationship, this being of the same support relationship, that relationship, as I intimated earlier, is an equivalent relation because it satisfies these three properties, again, which hopefully at least some of you will be familiar with, that constitutes whether this R, fancy R, is an equivalence relationship or not. So the first one is reflexivity. In other words, a volume of a certain support is obviously related to its, well, let's put it this way. The volume of a located or centered at S is of the same support as itself. And I think that's fairly obvious because in that case, your translation would be effectively the zero vector or a translation of zero in norm and in actual scalar terms. All right. The next one is symmetry. And again, that's fairly clear cut, that if a volume centered at S or located at S is of the same support as one that is located at S prime, it follows that the relationship occurs in the opposite direction, in inverted commas, that by the same token, the volume centered at S prime will have the same support as the volume centered at S. And essentially what you're doing there is one way of thinking about this is in the one case, you can use a translation of vector H, and in the other direction, you could consider a translation of vector minus H. And then lastly, the transivity. And that is basically saying that if one volume is of the same support as another, Vs is related to Vs prime. And in turn, Vs prime is of the same support as V of S double prime, then it follows that V of S, our starting point, will also be related to V of S double prime. So again, that's reasonably intuitive in the sense that if a volume centered at S is related to the volume centered at S prime, and the volume centered at S prime is the same, has the same support as one at a volume located at S double prime, then the two end members there, the Vs and the Vs prime, are of the same support as well. So that's quite a neat definition that my supervisor in France discussed with me, that support can be written in terms of the relationship of support can be expressed in terms of an equivalence relation. So that's the more formal, less hand-waving way of describing it in mathematical terms. So moving on to the next slide then. If we look at our good friend simple kriging, for instance, the matrix equation is given by the sample to sample covariances, or potentially variograms, multiplied by a weight vector for which we have to solve in order to determine an optimal, a best linear, unbiased estimator of the contribution of neighboring points to our target, is then equal to a sample to target covariance on the right-hand side. Okay, so that is the general structure of many types of kriging. Now, just to refresh to recall what was looked at before, is if the samples are of the same, now I'm going to be more formal and say of the same support as the target, then we are dealing with point, quote unquote, kriging. If, however, the samples are all of one support, but the target is of a different support, then you are dealing with block kriging. Okay, but the principle is the same. It's just how you calculate the covariances on the right-hand side. Okay, differing according to the support of the target. But where multi-support comes in, which I showed you towards the beginning of the presentation, is what happens on our left-hand side, when not all samples in their own right are of the same support. So it is here where your sample to sample, not only your sample to target covariances may be the result of different support, but there's nothing to say that the samples themselves are not of the same support. So in a nutshell, that is neither a point kriging instance, an instance of point kriging, nor of block kriging. It's in fact a kind of a amalgamation, or I don't want to say convolution is not quite the word, but basically it's somewhere in between. because the emphasis about point and block kriging is around how the target relates to the samples. But all those, as George Matteron, to get back to the gentleman we referred to before in conjunction with the work by Krieger, have always, or that seminal work that they did was always of the assumption that all the samples are of the same support, or at least they're approximately of the same support. And the only distinguishing feature, the only aspect that we have to be concerned with is how the support of the samples is relative to the support of the target. So effectively, what I titled my project was multi-support. It's previously been known as mixed support, but that in effect is generalizing not only the right-hand side covariances, but also the left-hand side covariances. And I just mentioned there that the elements of these matrices are covariances, and I could get into the stationarity assumption, second-order stationarity assumption, etc., etc. But I think the main issue here is there is something beyond purely point and block kriging. And as I've said a number of times, my feeling is that that terminology can be deceptive. So wrapping up now with my last slide. I think I probably finished a bit early, but I don't think you'll probably object to that. This is demonstrating the point here as I say, as a wrap-up slide, that your target, yes, in red, has a certain support, but then the samples can also have within them, there's a distinction of support between sample and target, but there's also a within sample distinction that is possible. In a nutshell, that not all the samples have to be of the same support. And again, I'm no longer using the term size or volume. I'm saying support, because what you're seeing there is, for one, you have a circular volume versus the majority of which are squares or rectangles. And you also have one sample whose spatial orientation is not the same as the others. So that sums up the idea in an intuitive sense, that dimensions are spatial orientation and shape all contribute to support. So for instance, if I were to attempt to translate, again, can you see when I'm moving the mouse?
Yes, perfect.
Okay, all right. So we're back to the original principle that if I try to translate this top left sample to this towards the bottom right sample, by virtue of the fact that there is an orientation, a difference in orientation, that vector translation or lag cannot be achieved, whereas this same sample here, compared to the sample on the bottom left, the one can be achieved from the other by translation, but with a different shape or different dimensions. That translation is not sufficient to make the one achievable through the support, this relationship of support. And therefore, as I say, that's a reflection not only of the idea of different supports, but again, and I've been mentioning that many times, that there's more to kriging than just the two basic assumptions of point kriging or of block kriging. So as I say, I have repeated quite a few concepts, but hopefully that does help you to take in the concepts more easily. On the other hand, I hope I haven't bored you with all this repetition, and I hope you do have some takeaways of what I've actually been the concepts of support that I've been trying to convey to you. And maybe if you are working in the geostatistical domain, or even possibly in the lattice domain, in future you might consider that there is more to kriging than just the basics as they were set up back in the 50s and the 60s. So with that, I'm going to say thank you, and especially to Inga for all the organizational aspects, and obviously her technical knowledge as well, of course. And yeah, if there are any questions out there, please go ahead.
Thank you, David. That was fascinating. I have many questions, but I'm going to ask the group first if they have any questions or comments. Nothing. Okay, I'll open the floor, then maybe. Ah, there we go. Ah, there was a hand. There was a hand. Where's it gone?
Sorry, Inga, you did mention that there's going to be a test afterwards, right?
Yeah. There's a big test afterwards.
Okay,
Yeah,
so obviously everyone fully understands what I've talked about.
100%.
That's why there are no questions.
Yeah, but I see Kathleen's hand is up. Kathleen.
Hi, David.
Hi.
Great. I think this was actually a really nice definition. It gives me some more material to confuse people when we talk about what support is. I actually liked the bit about bringing in the rotation, because a lot of people don't understand that they think the size is very important, but that rotation can actually kill an estimate very badly if you don't get it right.
Absolutely. Yeah, as I say, it's one of the aspects that does tend to be overlooked.
Yeah.
And quite difficult to take into account, David, surely, if you're doing the kriging.
Yeah, because getting back to that, my evergreen concept of point, what does become difficult is if your point, in inverted commas, is actually something like the square here that I'm pointing to. If, for instance, this red target area, or maybe, okay, let me rather take, for instance, this the circular, or the circular volume here. You cannot decompose the circle into a number of these squares, or vice versa, because the minimal, in inverted commas, support that I have in my data is the circle or the square. But if I were to try and calculate a covariance or a variogram value between them, I would have to use some form of an approximation, because you can't merge the one into the other, or you can't transform the one into the other. So in those sorts of circumstances, you would typically say, well, the square approximates the circle, and therefore, for the purposes of practicality, you could treat them as if they are of the same support, but purely for calculations. Realize also that if I am trying to construct an experimental variogram, again, I cannot use all of these points without due regard for support. So again, you have to partition, or should I say decompose, each of these targets into it's not really appropriate to say the smallest support, but hopefully you understand what I'm saying, the
Most
lowest
representative,
common,
maybe. Yeah.
yeah, exactly. So if you have the luxury, as you might have, for example, with this little square fitting into, hopefully 4 of those little squares will make up this larger square. In those cases, it's feasible to do some form of a discrete covariance calculation. But more generally, it can be more difficult, and there has to be, to make it feasible from a practical point of view, you will have to allow for some form of approximation. So this is where it would be nice if these were actually points, because if you have the point covariance, the real point covariance, then purely by integration, you can upscale it to any shape or form, literally. But at the back of your mind, you must always think in constructing your variogram or in constructing your sample to sample or sample to target covariances, you are not the smallest common factor, in inverted commas, item is not really a point in the sense that we would use it ordinarily. So again, you have to bear in mind all these aspects, because it is quite possible to make an estimate that is incorrect if you completely sweep the idea of support under the carpet and hope that your results will come out right. So remember, if you are working on a several $million project in whatever sphere of application it is, you potentially could give very wrong results where you just hopefully tend to ignore support and hope that everything will fall into place and nothing will be incorrect in your approach. Anyway, that's a very long answer to a short question.
I just want to confirm that what we're dealing with here is similar to lattice data, that the shape is represented by a single value. So it's aggregated, and the shape represents that that value represents the whole shape. Is that right? Or do we have multiple values on the shape?
Are you referring to what I call the S and the S prime, for instance?
Yeah, exactly.
Yeah. That's why I was saying there is a bit of some analogy to that. Sorry, carry on.
Carry on. I'm with you.
So there is some analogy with the lattice, because you would have this same kind of decomposition of overall area with sub areas or sub volumes. The terminology differs, or your aerial aspect. So yes, there is definitely a tie-in there, and I guess the term support could also be applied to the lattice data. It's just I think kriging and variograms are less likely to be encountered in a lattice scenario, as those tend to be aimed largely at geostatistical applications.
Yeah, exactly. And I think that, so it's actually very interesting. You've got lattice types areas or sample data, but it's not, so normal traditional lattices cover the whole area. So it's a full partition. Whereas here you've got lattice type areas in a continuous space where you're doing the kriging.
Yeah, exactly. So yeah, it's the domain. I guess one of the distinctions is the nature of the domain.
Very interesting. My PhD student is here. I hope she's listening and making notes, because she's doing her last paper for her PhD is discrete variogram estimation.
Okay, and of course the test that's coming up.
Yeah, and the test. Yes. No one can have a PhD unless they pass your test. Absolutely. Any questions from anyone else? This is very interesting. I like to have a nice technical talk now and again. It makes me very excited. Brings back my mathematics days.
Yeah, I hope I didn't flummox people too much with all the notation. I tried to explain it from a
very simple,
practical versus more theoretical.
I think it was very nicely done, David, especially because it is quite complex, but you explained why you're talking about it, and you give examples, and you give just enough theory, to cover the information. It was really great. Okay.
Thanks. Thanks, everyone.
Okay, no more questions. Awesome. Thanks, everybody. Thank you very much to David for his excellent seminar. And the yes, I see. You see Stefan's comment there, David.
No, yeah, that's the thing. I can't see the chat window.
He says, Stefan says, maths was well explained and definitely a wake-up call for us applied statisticians. I like it. You can't just ignore that little comment there in the R documentation. You have to actually understand what they're trying to say there. Very important.
For sure, yeah.
So, this was absolutely wonderful, David, and I'm so glad that we convinced you to give us a talk. We have another seminar because the year's running out and we want to pull them all in next Wednesday at midday with Dr. Sebnem from UCT. So please look out for that one. I also put it on LinkedIn if you missed it there, and it's also on the SASA website. And that one has got to do with road accidents. So modeling on roads, spatial modeling on roads. I think that will also be fascinating. So hope to see you all then. And I also hope to see most of you at SASA in 4 weeks' time. Thank you, David. Have a lovely evening.
Thanks, everyone.
Bye, everyone.
Bye, everyone. Bye.